welcome to today's tutorial. Today we will be learning about the Norton's theorem. So first of all, before we start, let's try and note the difference between the Thevenin's theorem and the Norton's theorem. You remember in Thevenin's theorem, we calculate for what? Two terms. Let's say this is Thevenin and this is what? Norton. So Thevenin's theorem, we have to calculate for the Thevenin's voltage and the Thevenin's what? Resistance. So we calculate for VTH and what? RTH. But then in Norton's theorem, we are going to calculate for Norton's what? Current and Norton's resistance. So we have Norton's current IN and Norton's resistance what? RN. And we also learned in Thevenin that the Thevenin's equivalent voltage VTH is an open circuit voltage, because the load that we removed, whenever we remove the load, that portion becomes open, and that is where we find what? The VTH. So the VTH is an open circuit voltage. So VTH is what? Open circuit voltage, OCV, open circuit voltage. But then in Norton's, when we are finding what? IN, Norton's current, we also have to remove the load. The procedure is similar to the Thevenin. We have to remove the load from the circuit. But after we remove the load, we are not going to leave that portion open. But then we are going to what? Short circuit that portion and find the current on the short circuit. So we also say that the Norton's current is also the same as the short circuit current. So we have something called the short circuit what? Current. Norton's current is a short circuit current, whilst Thevenin's voltage is an open circuit voltage. And also for a given network, a given circuit like this, the value of our Thevenin's resistance, RTH, is the same as what? The Norton's resistance. So if you have a given circuit, the value of your RTH will be the same as what? Your RN value. They are the same for a given circuit. Alright, good. So Norton's approach is similar to the Thevenin, just that we are going to find IN instead of what? VTH. That's the difference between the two, the main difference. And we also know that the Thevenin's equivalent network is a series network. Why? Because when we get the VTH and the RTH, we draw a series network having the VTH connected to what? The RTH. They are in series. So the Thevenin's equivalent network is what? A series network. But for Norton, when we calculate IN and RN, we are going to draw a parallel network. And in that parallel network, our source is going to be our RN, and the resistor is going to be what? The RN. So we can say that Norton's theorem is what? A parallel network. That is the Norton's equivalent. It's a parallel network, but the Thevenin's equivalent is a series network. So let's see how we can use the Norton's theorem to calculate the current flowing through what? This 4 ohms. Let's see. There is also one thing you have to note about the Thevenin's and the Norton. You realize that the Thevenin's equivalent of a given circuit is like this. So we have VTH and what? RTH. Okay, this is the Thevenin equivalent of a network. So if I want to find the Norton's equivalent, I need IN. But I can see that this voltage is in series with what? This resistor. So back to our idea of what? Source transformation. A voltage in series with a resistor can be converted to what? A current in parallel with that resistor. So it means we are going to have what? A current source for this one, moving up. And that current source is going to be what? Parallel with the resistor. So we have this resistor being what? RTH. And now we have what? A current source I. So we are saying that that current source here is going to be our what? Our Norton's current. So we have what? IN. So we can easily say that the Norton's equivalent circuit is the source transformation of the Thevenin's equivalent circuit, or vice versa. That is, the Thevenin's equivalent circuit is also the source transformation of the Norton's equivalent circuit. So if you are good with what? Your Thevenin, you can find your VTH and your RTH. And when you are asked to find the Norton's current, you just have to divide what your VTH by your RTH and you get that current, and that is your Norton's current. So this IN from Ohm's law, I is what V over R. So the V is what the VTH over the RTH, and that one will give you what your Norton's current. And don't forget, we said our RTH is equal to Rn. So the value here RTH can be the same as what our Rn. So this is the Norton's equivalent, and it is just the source transformation of our Thevenin's equivalent. Good. So we are going to use this diagram to calculate our IN and Rn. Our IN, Norton's current, and what? Rn. So first of all, let's see the fixed portion of the network. This is the fixed portion without the load. This is what the fixed portion. So we will first of all remove the load from the network. So the load is 4 ohms. So we remove the load. So let's draw the diagram without the load. I have a source here. I have this one here. I have this. I have that 10 and this. So let's see, this portion is what? 10. This portion is 10 ohms, 8 ohms, 6, 2 and what? 28 volts. So if we are doing Thevenin, after removing the load, we have to maintain here to be open, then find the voltage VTH here. But Norton is saying after you remove the load, you have to short circuit that terminal. Don't leave it open. So we are going to short circuit the terminal like this, and we are going to find current on that short circuit. So there will be a current moving on that branch. That is our IN, the short circuit current. But that current it will move in a direction, whether it is going down or up. You just can't put it there anyhow. It should be based on what? The source in the circuit. So if this is our source is moving current in that direction, here, current will get here, it will split here and here. So current in the 10 is moving like this, which means the current on this branch that we are trying to find is the same as what the current flowing through this 10, and it is moving down. So the current here, the Norton's current IN, is moving down, and you can see that IN is what the current moving through the 10 ohms. In Thevenin, you realize that when you want to find VTH, you have to consider some resistors. You want to get their voltages, and that voltages will help you get the VTH. The same thing applies to Norton. You have to take a particular resistor. You see that the current in that resistor will be what? Your Norton's current. And you realize that the current moving through this thing is moving through what? This branch, which is our IN. So our job here is to do what? Use this diagram, calculate current for what? The 10 ohms. And that one will be our what? Norton's current. Very simple. Very simple. So let's see how we can get what? The current flowing through the 10. Someone will use the network reduction method, which is very simple in getting the current for the 10. So for me, I will try and apply what? The source transformation that we learned in this question, because it will make things easier. Check first if you can use. I thought I can use it, not realizing that this voltage is parallel to this, so I can't transform. It should be in series before we can transform, so we can apply the source transformation. But we can use our what? Network reduction. That is the series parallel combination. So let's see, starting from the end, you can see this 10 and these 8 are in parallel. So let's find its equivalent. Let's call it RA. We have to do a lot of calculations here. So we are just trying to find current in the 10. So 10 and 8 in what? Parallel is giving us 10 by 8 over 10 plus 8, which is what? 80 on 18 as what? Our RA. So let's do some small cancellation. Let's see. We have what? We have 80 on 18, and that one is giving us what? 40 on 9 ohms. So 40 on 9 ohms is the equivalent here. So that resultant, that equivalent there, will be connected in what? Connected in series with the sys. So we can as well draw something to show, so that we can see it clearly. So we have this here, we have this there. Good. So our 40 on 9 is here, our source is here, our 2 is there, and this is what? 28 volts. So we can decide to find total current, then use the current divider rule to get what? The current in the term. Very simple. So let's see. From here, what can we say? We can say the source and the 40 on 9 are connected in what? Series. So RB is equal to source plus 40 on 9. And that is giving us, let's punch it together. So source plus 40 on 9 is giving us 94 on 9. 94 on what? 9 ohms. That's the equivalent here. So let's draw. We have this here. We have this one there. And we have 94 on 9 ohms. We have 2. We have what? 28 volts. So what else can we see? From here, the elements are all connected in what? Parallel. The 28, the 2, the 94 and 9 are in parallel, so they have the same voltages across. So we can use the idea of elements in parallel. So the voltage across the 94 and 9 is also what? 28 volts. Let's say V 94 and 9 ohms is what? 28 volts. So ask yourself, which element did we combine to get this? We combine source and 40 on 9 in series. So we can apply the voltage divider rule because they are in series and get the voltage for this, because that's where we'll get the 10. So voltage for 40 on 9, voltage for 40 on 9 is equal to what? 40 on 9 over source plus 40 on 9 times what? 28 volts. So let's take our time and go through step by step. So in this case, we have 40 on 9 divided by source plus 40 on 9 times 28. And we are getting 560 on 47. 560 on 47 volts. Let me check correctly. 560 on 47 volts to be the voltage across this 40 on 9. So last thing, which element did we combine to get this 40 on 9? We combine what? 8 and 10 in parallel, meaning the voltage for the 8 is this, the voltage for the 10 is that, and I need what? The current for the 10, which is my IN. So current for the 10 IN is the voltage over the resistor, and the voltage is 560 on 47 divided by the resistor 10. So we have this divided by what? 10. So answer, so we have 560 on 47 divided by what? 10. And that one is 56 on 47. 56 on 47 amperes. So our Norton's current IN is equal to what? 56 on 47 amperes. Now, we have to calculate for what? Rn. And as I said, calculating for Rn is the same as calculating for what? RTh. So we should not see any source. All sources should be deactivated. So we are going to deactivate what? The voltage source. We have these two here. We have this source this is what 8, this is the 10. So this is where we are going to calculate what Rn. So 10, 8, 6, 2. Looking in that direction, we are going to calculate our Norton's resistance. So as we said, let's assume there is a current flowing on one of the branch. So if there is a current flowing from here, it will pass through the 10. The current will split between 8 and 6. The current will get to this junction. It will avoid these two, move through this short circuit, then return back. So the 6 and the 8 and the 10 are what we are going to consider. So we can see 6 and 8 are in what? Parallel. And its equivalent here will be in series with the 10, and that will be our Rn. So our Rn is what? 6 by 8 on 6 plus 8. The equivalent in series of what? The 10. And we are getting, so let's punch it together. So we have 6 by 8 on 6 plus 8 times plus 10. And that is given 94 on 7. 94 on 7 what? Ohms. So we've calculated for IN and RN. The last thing to do is to draw the equivalent what circuits, which is a parallel network for Norton. So that parallel network, our source is what? The current source. The IN we've calculated for. And the RN will be what? Parallel to it, like this. And this is the terminal we are going to connect with the load that we removed. So we are bringing back the load, which is 4. So 4 ohms, Rn, and what? In. That's the Norton's equivalent circuit. And we are asked to calculate I naught in the 4. So you see that for us to get the current in the 4, we have to apply what? The current divider rule, because it's a parallel network. So using the current divider rule, I naught is equal to what? The opposite, which is Rn. So 94 on 7 divided by what? 94 on 7 plus the 4 times the In. And what did we get? 56 on 47. So 56 on 47. So we have to punch this and calculate the current I naught. So 94 on 7 divided by 94 on 7, we have plus 4. And this one is being multiplied by what? The 56 on 47. So that's giving me 0.918 amperes. 0.918 amperes. So I remember in our Thevenin's theorem video too, we calculated for the current in the 4 and we had what? 0.918 amperes, which is the same as the Norton's theorem. So this is the end of this tutorial video. In our next video, we will solve more questions using the Norton's theorem. Thank you very much for watching this video.